Hello, we are the College Station Cavaliers. This is Project 1 Logic Locking. The group members are Zeina, Adrian, Jacob, and Sanchez, and Griffyn. So the motivation for this project. In the semiconductor industry, intellectual property is extremely important. Companies spend millions of dollars and years to work to develop, test, and launch a new integrated circuit. If the design of a chip gets leaked, serious consequences will follow. For example, if a rogue foundry can take the leaked design and manufacture it on their own and sell it for a lower price, this will significantly reduce the total amount of business a company will obtain in the lifetime of their new device. To prevent these forms of piracy, companies spend equal efforts hiding and protecting their design logic to make their products less vulnerable to attacks. So how is this done? There are many ways to protect an IC from attacks. However, specifically in this project, we will be looking into stripped functionality logic locking, or SFLL. SFLL is a promising new state-of-the-art technique that preserves the design of an IC by intentionally stripping the functionality of the chip to protect it against reverse engineering in the manufacturing stage. After the chips are manufactured and in a safe space, a key is applied, which returns the functionality to the device. After this key is applied, the device will operate as expected and is ready to be sold in the market. By applying this logic locking, companies can feel more confident that their designs are to not be stolen in the most vulnerable parts of manufacturing.
Here's a high-level diagram on SFLL and the processes that occur. So firstly, the IC is logically locked and some functionality is removed so that the design cannot be reverse engineered or replicated. The second step is that the design is sent to be manufactured at a foundry. Companies such as Intel, AMD, and NVIDIA participate in this from an in-house design and external manufacturing. The third step is that once the chip is manufactured and ready for the company that designed it, a key is applied to the chips which returns the once stripped functionality. The final step is that the device is fully operational and ready to be sold in the market.
For this project, we completed tasks 1 through 6 to build up to our final task of performing logic locking on an open source processor. To start, we used the Berkeley ABC tool to convert bench circuits that were provided to us in Verilog. This exercise helped us become more familiar with the bench and Verilog format for some basic. To start, we used We also were given an example of logic-locked Verilog and were able to use this to manually implement logic locking on some of the smaller benchmarks, giving us a basic understanding of how logic locking works. Our next step was to create a Python script that would perform the above steps automatically so that we could perform logic locking on any size of a benchmark circuit. Our Python script takes the original provided bench file and outputs a logic-locked Verilog file, automating the logic locking process and making it more efficient.
We also learned how to use the Synopsys Design Compiler, a tool used for Verilog synthesis. This tool takes any format Verilog file and converts it to a netlist, which is a synthesizable and simplified format. It also generates an area, power, and timing report. This is useful for real-world applications since designers want to make the simplest and cheapest circuits so behave the same way. Our next task was to create a Python file to automate the conversion from netlist Verilog to bench format, similar to one of our previous tasks. Our script takes the Verilog netlist generated by the design compiler and outputs a corresponding bench circuit. We verified that this steps work for our logic-locked netlist with no errors, meaning we could generate logic-locked bench circuits using our design compiler outputs. Finally, we verified that our logic-locked bench circuits were functioning successfully. We used the lcmp command, which compares an original bench file and a locked bench file when given the key input. It shows how the two circuits are different. With the correct key, the two circuits should be the same, and with the incorrect key, they should be different. We verified that this was working properly, and our results are included in this slide. We also ran an SAT attack on our locked Verilog using the SLD command. This tool shows how many iterations it would take to break the circuit and return the key value. These results are also included in the slide. Our final task was to perform logic locking on an open source processor, which we will be showing for our demo.
First, we had to install the CVA6 processor and an SoC using the shell script provided. Then we performed logic locking on one part of the processor using the schematic on the slide.
To run the processor, we used a script and a test file that create an output log file. We ran the processor with both the correct and incorrect key and compared the output log files to make sure that the locked and unlocked processor had different outputs. But these are both included in the slide, so you can see that when the key is correct or incorrect, the trace files are different. So now we're going to demo that. So first we can look at the decoder file, which is where we made the edits to the processor. So all of the edits are right here. This user key part is where we provide either the correct or incorrect key. So right now, the processor has the correct key. It's already been compiled, so we're going to run our processor with the locking and the correct key. So now that our processor is done running, we opened the trace file, and we can see that everything is behaving normally because we used the correct key. So now if we go back to our decoder file, and we edit the key to make it the incorrect key, we're going to rerun the processor and we'll see that the trace files will be different. So now we're going to use the incorrect key. We're going to recompile also. So now the processor is compiling, and once it's done, we'll rerun with the wrong key. Now that our processor is done compiling, we're going to rerun the processor to generate the log file. So now that our processor is done running, we can look at our trace file. And now that we use the incorrect key, we can see this line here, the exception caused legal instructions. So basically that verifies that our processor functions differently when it's given the correct and incorrect key.
This project enabled our team to learn valuable information regarding logic locking. We gained a deeper understanding of logic locking techniques, particularly stripped functionality logic locking, and how it enhances the security of integrated circuits by stripping some functionality of the design and hiding it from the user until the secret key is input. This project presented new learning opportunities to all team members. We developed a deeper understanding over SFLL techniques and how to perform logic locking to strip functionality from an IC. Our semester-long learnings enabled us to perform SFLL on a RISC-V processor and verify its success using trace file output.